Welcome to the shape of space matrix calculus. In this lesson, I'm going to talk about dual numbers. We'll apply those to derivatives as linear operators. I'll give a few examples, and I'll also mention the Fréchet derivative along the way. In what follows, we're going to use something known as dual numbers to define derivatives as linear operators. Dual numbers are also used in something known as automatic differentiation. We're not going to get into automatic differentiation, but just in case you have heard of that, I wanted to make the association there. So dual numbers are just, let me point to these. Dual numbers are formed as pairs of real numbers, with addition being component-wise, and multiplication defined by the formula given below. So here we have two dual numbers, and if we add or subtract them, we just do it component-wise, as shown here. Multiplication is a little bit strange because the first term is just a times c, but the second term is this unusual expression ad plus bc. And I'll explain or give you some motivation for that in a second. The dual number epsilon is defined as the pair 0, 1, and it has the property epsilon squared equals 0. So this is a little bit reminiscent of complex numbers where you have I and the I squared equals -1. So it's not exactly the same, but it kind of reminds me of that. So alternately, we can express dual numbers in the form a plus b epsilon. And we can also do multiplication using this definition or this alternate form, which I'm showing here. So AB times CD. The first, you get AC here, and then you get AD times epsilon and BC times epsilon, this middle term. Then you get BD epsilon squared. But epsilon squared is 0, so this drops out, and what you're left with is this. And notice it's AC for the first term, and then AD plus BC for the second term. You can also do division. So AB divided by CD, multiply top and the bottom by C minus DE. Again, this is kind of reminiscent of how you would divide complex numbers. Multiply the bottom out, and you get this here. Multiply the top, it's basically what we did up here. Get this here. And then epsilon squared is 0, so this cancels to 0, this cancels out, and you get this form here. And if you like, you could go one more step. You could write this in the a plus b epsilon form. So it would be a over c plus bc minus ad over c squared epsilon. And this all holds if c does not equal 0. Consider a differentiable function f from r to r, and assume we want to find or evaluate the function at x plus be, the dual number. Given that f is differentiable, we have this Taylor series for f given by this formula. So at point x was perturbation h. Sometimes you'll see this written as instead of h, delta x. So in order to find x plus b epsilon, we have to plug in b epsilon for h, which we'll do here. But then keep in mind that epsilon squared is 0, and that means that epsilon cubed and epsilon to the fourth and so on are all equal to 0. So we plug in b epsilon into here for h. So we get f of x, then the derivative of f of x times b epsilon. And then all the other terms have epsilon squared or epsilon cubed, or so higher powers. So these all drop out, and then you just get f of x plus b epsilon equals f of x plus the derivative of f at x, b times epsilon. If we let b equal 1, we get this first formula here. And if we just take the difference, subtracting f of x from the right to the left, then we have this here. And I want to point out that this is analogous to the differential. df equals the derivative of f of x times dx. So this is analogous here. This is exact in terms of the dual number, but in terms of the differential, it's just approximately equal to the difference. So here, epsilon serves as an algebraic representation of an infinitesimal perturbation similar to dx, but with the rigorous framework of dual numbers. The nilpotency of epsilon, in other words, that epsilon squared equals 0, ensures that the Taylor series truncates exactly after the linear term. In other words, all these terms go to 0, providing an exact expression for the derivative without higher order terms. Okay, so this is, in terms of dual numbers, this is exact. In terms of differentials, it's just an approximate for the differences for d of x small and close to x. All right, we're going to make a lot of use of this later, so I'm just kind of setting you up for some additional theory that I'm going to get into. Okay, so keep this in mind and let's continue. The dual number concept can be extended to vectors, and we define the operations as shown here. We take a vector v, just the sum of a plus b epsilon, and u, the sum of c plus d times epsilon, where a, b, c, d, u, v are all vectors in Rn, and epsilon squared is 0 as before. It's not a vector, it's just this abstract entity that 1 squared equals 0, and we attach it now to vectors. So if we add u and v, or subtract, we just add the what's called the real part, first part here, and then we add or subtract the dual part. We get this here. And then multiplication, dot product, u dot product, v dot product u would be a dot product with c plus, then you'd have a dot product with d plus b dot product with c times epsilon. Then the other term, which drops out, b d epsilon squared, that would be 0. So that's why it's not part of this formula. Then we can do something very similar for matrices. We take a matrix A that equals A1 plus A0 plus A1 epsilon, where A0 and A1 are matrices of the same size, and epsilon is, as before, is a formal symbol satisfying epsilon squared equals 0. And A0 is the real part, and that's the terminology is used for the vector, dual vectors, as well just as dual numbers, or standard part. And then A1 is called the dual part or the infinitesimal perturbation. Okay, and if we take two dual matrices shown here, we add them, or we could subtract them by component. We just add the real parts together, and then the dual parts shown here. Scalar multiplication is you just multiply through by c. And keep in mind, epsilon is not a vector and it's not a matrix. It's just this entity that 1 squared equals 0. And then multiplication is similar. If you just multiply these as you would with matrices, you would get A0, B0, and then you get A0 times B1 times epsilon, and then A1 times B0 times epsilon. And then, of course, the last one here, A1 times B1, epsilon squared, that's 0. So that's not part of the definition of the multiplication. Okay, so we can extend the idea, and again, this is useful in various computer applications where we're computing derivatives. The gradient and Jacobian are what I think of as interior techniques. That's my own terminology. These techniques are more appropriate when we're given the internal details of the scalars, vectors, and matrices that define the input and output of a particular function. So the examples we saw in the previous lesson and what you would normally see in the calculus course and multivariate calculus are of this type, where you're using these interior techniques. In other cases, for example, if we have f of x equals x transpose a x, where a is a matrix and x is a vector, you could use these interior techniques to find the solution. You would expand this out, giving names, x1, x2 up to xn for the vector x and its transpose. Then you would name all of the components of a. You would take partial derivatives to form the gradient, and then you would look for a pattern to in terms of how to express the result of the derivative. Very, very long, hard methodology. For things like this, we'll use approach that doesn't involve getting into the internals of the matrices. We'll just manipulate the matrices and vectors, and this is what I call an external technique. You'll see what I mean. It might be a bit hard to appreciate here at this point, but I just wanted to kind of state this leading into it. Where the general idea is you're going to have functions that are combinations of vector and matrix multiplication, add it together, subtract it, so forth. In a lot of cases, it's easier to take an external approach where you never actually look inside of the vectors and matrices, but you use other characteristics of the vectors and matrices to find the derivative. And we'll see some of that in this lesson. In single variable calculus, the derivative of a function f of x is defined as the slope of the tangent line to f of x at a point x, f of x, point x, f of x, this point here. You should know that from basic calculus. What I want to do is generalize this so we can have something similar for vector and matrix functions. It's going to take several slides to explain this, and there's also a YouTube video from an MIT class that has a very similar development, so you may benefit by having a second presentation of the same material. The way I'm explaining is a little bit different from the MIT class, but it's the same general idea. So I'll give you a link to that in case you want to see an alternate presentation on similar material. So let's continue. Further, the derivative of f at x can be used to approximate a change in f of x, denoted by delta f, relative to a change in x, denoted by delta x. It's given by this formula here. This is the exact change, and then this is also exact, except the way it's written, it's the derivative of f at x times delta x, and then this thing here, which is called little o of delta x, or these are higher order terms. They come from the Taylor series. So they're things like delta x squared, delta x cubed, delta x to the fourth. They go to zero very quickly, more quickly than delta x. And they're typically ignored or explained away in different presentations, which I'm going to actually do here also. So more formally, the notation little o of delta x denotes any function whose magnitude shrinks much faster than the absolute value of delta x is delta x goes to zero. And I have an example here for the absolute value of delta x raised to alpha. This is, in fact, little o of delta x if alpha is greater than 1. And the way you test that is by taking the limit. You take your candidate function that you think might be order little o of delta x, and you divide by the absolute value of delta x and take the limit. I'm doing here, and then you get alpha minus 1. Since alpha is greater than 1, this limit goes to 0. In differential notation, we have something similar to what we're showing here. The differential of f of x is defined like this. And this represents the linear part of the change f of x plus dx minus f of x. The full change is given here. It's basically this linear part and then these higher order terms. So we're just using differential notation. It's analogous to what we had here. But this is leading to the definition of an alternate definition of derivative that I will get to in a second. And then going from this line to this line, I just substituted this in here. So however, in differential notation, we neglect, or we often neglect, the little o dx term as it vanishes for infinitesimally small dx. With this caveat, we take derivative of f of x in the context of the following equation as our definition of the derivative of f of x. So if we take this difference here, and what's on the right of it, or however you want to put it on the left too, you can do it. But whatever this equals, if you can break it down into dx times some function, then that function is the derivative of f of x. And I put the approximation sign here because of we've taken off this term, but I'm going to not continue using this approximation. This is just to be technically correct initially, but I'm going to remove this. And in fact, when we have an analogous definition using dual numbers, and in the case of dual numbers, this is not even approximate, it's exact. You'll see that in a moment. I took the last equation from the previous slide and I slightly rewrote it. I removed the df, the differential, and the approximately equal sign, and I just want to work from this equation here. In this formulation, we avoid dividing by dx. This is critical because if you use the notation from calculus, dy dx equals the derivative of f of x, it doesn't extend where dx is a vector or even a matrix. So in this form here, you can have dx as a vector or a matrix. Derivative of f of x would be a matrix, for example, and this could be a vector, and everything works out fine in that case. So that's why we went through all the trouble of restating the derivative. In terms of dual numbers, we can rewrite this. Let dx, or let epsilon equal dx, and x plus dx equal x plus epsilon. And then we get, we can restate this in this format here. But the key point here is this is actually equal, because when you substitute in epsilon for the higher order terms, as we saw when we did the Taylor series earlier, they all drop off to 0. So using dual numbers, this is actually exact. Okay, so that's one thought, and now I want to continue along these lines here. From the perspective of linear algebra, the derivative of f of x can be viewed as a linear transformation applied to dx, which I'm writing out here. So I just took this and I emphasized that this derivative is being applied to dx as a linear transformation. And then we can test the linearity here. If we take a plus dx sub 1 plus b times dx sub 2, then that's just this here, but that's the rule that you need to satisfy to be a linear transformation. So more generally, we can view the derivative of f of x as a linear transformation that takes an input direction vector v and gives an output vector derivative of f of x applied to v. Now this is no longer an infinitesimal, but the formula still works if you put a directional vector in here. So which can be interpreted as a directional derivative, as discussed below. I have a separate slide on directional derivative. I'll get to that. When the directional derivative, when the direction v is an infinitesimal dx, the output is the differential, this thing here. So, i.e., the infinitesimal change in f of x corresponding to dx. In what follows, we will usually write the derivative f of x dx and drop the brackets referring to this here. But just wanted to make the point that it's also a linear transformation, and it meaning our new definition of derivative. It's also a linear transformation, and it can be applied to yet other vectors than just these infinitesimals. I have an example. Find the derivative of f of x equals x cubed using the dual number formulation of equation 1. So we have f of x plus epsilon minus f of x. So you have x plus epsilon cubed minus x cubed. Then expanding this out, it's all these terms here, minus x cubed. Then the x cubed and the x cubed cancel. Then x squared is 0, epsilon squared is 0, epsilon cubed is 0, and you're just left with this one term here. And so by our definition, whatever is multiplied, if we do this calculation, whatever is multiplied times epsilon, in this case 3x squared, is by definition our derivative. And we know that from basic calculus that in fact that is the derivative of x cubed. All right, let's look at a little bit more complicated example in the next slide. Find the derivative of f of x equals sine x using the dual number formulation of equation 1. So we're going to take a similar approach to what we did in the previous example. We'll need to use the Taylor series for sine x to do this. So we start with capital DF equals sine x plus epsilon minus sine x. Then this is the Taylor series for sine x, and this is the Taylor series of sine x plus epsilon. Then we write both of these out, expand them out in detail. And there's a lot of cancellation to get down to what we have here, and I'll explain that in a second. And when you, accepting that this cancels to this, when you factor epsilon out, then you're going to get 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial minus x to the 6th over 6 factorial, and that's actually the Taylor expansion for cosine x times epsilon. So this, by our definition, equals the derivative of sine x times epsilon. So cosine x is our solution, and we know from basic calculus that that's the case. Okay, so let's just quickly review how all these things cancel to give us what's here. You notice the x and the x cancel, and then if you take the first term in this expansion, it's x cubed over 3 factorial, and you have a plus version of that here, so they cancel. Then you get the first term of this is x to the 5th over 5 factorial, and that cancels with this. Okay, so all those terms cancel out. In fact, this whole thing cancels out with the first term in each one of these. And then what's left are the powers of epsilon times some power of x. And the powers of epsilon greater 2 or greater all go to 0. So you're just going to get one non-zero term in terms of the epsilons here. And for the first one, if you multiply this out, as we saw the expansion of that on the previous slide actually, you're just going to get x squared epsilon over 2. You're going to get, 3x squared epsilon over 3 factorial, and the 3 cancels, and you just get this here. And if you expand this out, and we know the first term gets canceled with this, and then all the other terms have some epsilon in it, and the only one that survives is the one that only has epsilon to the first power, that's times x to the fourth, and that is 5 actually times x to the fourth, which cancels with the 5, and it gives you 4 factorial down here, and then so on. So you have this pattern. There's another approach, is to use the double angle formula for the sine function. So again, we start as we did here. We have this, and then we apply the double angle formula to this here, which is what I've written out, minus sine. And then it turns out this first term is just sine x because the cosine of epsilon is 1. And then the second term, the sine of epsilon is epsilon. So you just get cosine x times epsilon, and then you have minus sine. And then the sines cancel, and you get cosine x times epsilon. So you get the same answer again. So how do we go from, how do we get this here? Cosine epsilon equals 1, and the sine of epsilon equals epsilon. So that came from the Taylor series. So here's the, see, we'll look at it here, I guess. This is the Taylor series for sine. And if we put an epsilon here and for x, then all these other terms just go to 0, and you just get epsilon. So that's from this. And then pulling the epsilon out of this, this is the Taylor expansion for cosine. And when you plug in epsilon, these terms will go out, and you just have a 1 here. And that gives you this here. Okay, so mainly I did this to emphasize the point that this alternate definition works. This is not the easiest way of doing it, and this is further complicated or diminished by the fact that I had, in order to get these Taylor series, you need to have derivatives to derive to get these. So again, it was mainly here just to illustrate the point that this works. You'll see when we get to vector and matrix calculus, this is in fact useful, but I just wanted to start easy with doing some simple examples from basic calculus here to show that you get the same answer using our new definition. It's possible to interpret the linear operator view of a derivative as a directional derivative. I mentioned that earlier, and I just wanted to do a little more detail on that here. So consider a function f of x, where x is a vector. The directional derivative at x in the direction of vector v is defined as the partial derivative of f of x plus a times v, evaluating a at 0, and that in turn equals the limit is delta a approaches 0 of this expression here. And this is a bit unusual from what we know from basic calculus here, in that we're approaching x on a particular vector. If you just have a function from the real numbers to the real numbers, and you want to take the limit as you're approaching a particular number x of f of x, you can only approach from the left or the right. Now, when you're in multiple dimensions, you can approach along a multitude, an infinite number of vectors, and that's what's defined to be the directional derivative. For the derivative to exist outright, then you would have to prove that over all possible directions, this thing exists, this quantity exists, which we're not talking about on this slide, but just to point that out. We can also normalize the vector v to have length 1. That's not critical to the discussion, but I mentioned that here. On the other hand, if we use the linear operator definition, or equation 2, which I copied up here, then we have f of x plus dAv minus f of x equals the derivative of f at x, and then we just plug this in here, and then we can take out the dA because it's a scalar, and we get this, and then we can divide dA into this side here, and we have the derivative of f evaluated at x and applied along vector v equals this here, which is essentially the same as this. And so we have equating this equation with this equation, we have this So basically the directional derivative defined formally here is also equal to our interpretation of the derivative of x applied to a particular vector. Okay, so that's the directional derivative. I have another concept on the next slide I want to talk about. Let's get to that. In the following lesson, we will extend the definition of the differential in equation 1 to functions that take a vector input. In support of this goal, we need to talk about something known as the Fréchet derivative. It's a little bit complicated, but the conclusion is, I hope, not too hard to understand. So let V and W be normed vector spaces, and let U be an open subset of V, a function from F from U to W, where again U is just an open subset of V, is said to be Frechet differentiable at X, an element of U, if there exists a bounded linear operator A from V to W such that this limit exists here. So it's the dx is approaching 0, and we're using the norm defined on the vector space V. That's what the little v down here means, and that means the same thing here. And then on the top we have this difference, so it's f of x plus dx minus f of x minus this linear operator times dx, and the norm here is in the codomain for the vector space W. The above limit is meant in the sense of a limit of a function defined on a metric space that induces these norms with V and W as the two metric spaces. Equivalently, and this is what I want to get to here, and in the form that we will use, the following first order expansion holds. So this can be represented this way here. The differential equals f of x plus dx minus f of x, and that in turn equals a dx plus some higher order terms, which we will ignore. So most importantly, if such a linear operator exists, so if we can take this, if we're given a function and a vector function, and we can get it in this form here, then this a is the derivative of f at x, and not only that, it's unique. So the trick is, if we were given these vector functions, is to try to reduce it into this form and then just read off the derivative. And from this theorem, Frechet's theorem, we know that it's unique. So there's some properties that I want to talk about in this related to this definition, and I have that on the next couple of slides. The theorem we had on the previous slide is more general than we need. For our purposes, the vector spaces V and W can be Rn, although the n doesn't need to be the same for both V and W. Frechet differentiable functions follow these three properties here. The derivative of a scalar times the function is the scalar times the derivative of the function. Then the derivative of the sum is the sum of the derivatives. And you can combine these two together and just take a derivative of a linear combination, and then that would have the expected result. The chain rule holds true in this context, but we need some conditions. If f maps from vector space V to Y is differentiable at x, an element of an open subset of V, and G is a function that maps from vector space Y to W is differentiable at Y equals f of x, then the composition of G with f is differentiable at x, and the derivative is the composition of the derivatives. So G of f, the derivative of that at x, is the derivative of G evaluated at f of x, which we know exists because of this condition here, the composition of that with the derivative of f of x. You may notice there's no product rule here, unlike what we have for the single variable calculus. That's the reason for that is, in general, Vector spaces don't have the product defined between vectors, so we don't have that. We also don't have the quotient rule for similar reasons. And then these three properties here hold true for the differential df that we defined in equation 3 from the previous slide. So what we're going to do in the next lesson is use our definition here, typically equation 1 or 3, sometimes equation 2 from this lesson, and we'll apply it to different cases.